Hello, in this video we're going to talk a little bit about early Chinese mathematics and the 10 classics. So the most important of these 10 classics is the 9 chapters on the mathematical art. You can see a picture of a portion of it there on this first slide. So China was one of the earliest regions to develop an advanced culture, so it has very ancient and deep tradition there. It's not as old as Mesopotamian and Egyptian culture, and civilization there, but it's around the same age as the Greek civilization, so still very ancient. It started in the region between the Yellow and Yangtze rivers and expanded to include what is now present day mainland China and beyond, with the the amount of control varying as different dynasties took over and the region was fractured into smaller groups or unified into larger groups as different people took control of the region. Now, there were a few different ethnic groups in the region, but eventually they were kind of all absorbed into a general Chinese culture. And that was fairly isolated from outside influences for a long time. A lot of that's because of the natural mountain barriers and mountain and sea barriers and so forth that kind of kept it isolated a bit. And of course, like everywhere else, mathematics developed in China, but there it developed mostly independently from influence from outside. So there was probably some contact with Indian mathematics from time to time, but it took quite some time to have some contact with more Western mathematics. So it kind of grew up with its own flavor. And ancient and medieval Chinese mathematics definitely had its own characteristics that were quite a bit different than, say, the Greek, uh, Greek, Muslim, European tradition. Let's see. Chinese mathematics does not follow the axiomatic theorem proof style developed by the Greeks. Now, they did have proofs of a sort, or at least justifications, but not what we would probably call a proof in our modern sense. So, for example, they had something that they call the Goju rule, which is the same thing as the Pythagorean theorem. And they would have provided a picture basically like this, or they did provide a picture something like this, and say, well, that proves the theorem. So nowadays we would say that picture on its own doesn't actually prove the theorem. You'd have to prove that all the parts have the sort of right characteristics, that you actually have a square there and you have rectangles and you see, I guess I see 3 squares there and some right triangles and so forth. So you'd have to prove that those things actually have that and that you could actually do such a construction. That would be a more modern style of proof or a more Greek style of proof. But nevertheless, they understood why the Pythagorean theorem worked, or their version of it. And so there were some justifications. Their, a lot of their work, especially what we have passed down to us, was problem based, basically word problems, um, application problems, things like working with calendars, trade, land measurement, architecture, government records, taxes, things that people actually needed to use mathematics for, and they came up with techniques for them. But they did have folks that were more innovative and that they worked beyond these basic just problem solving techniques and thought about mathematics quite a bit more deeply. So they had some very true mathematicians, okay, just like the Greeks did, but just a little different style. So let's talk a little bit about the 10 classics. The 10 classics were a group of books that were collected and formed the basis of their mathematical curriculum. Now, they were developed over a very long period of time by multiple authors. Some of these We don't know who the authors were. Some of them we do. Some of them we know when they're written. Some of them we don't. Some of them were collected and updated by various authors. But in the early 7th century, a mathematician named Li Chongfeng was charged with collecting these important works together. And this is the list of the 12 works that he collected in this collection. And he also edited them to uh, um, remove some errors and in some cases added some clarity. They were named the 10 classics in the year 1084. So obviously they could count to 10. So I'm assuming that at some point between the original collection of 12 and the collection that ended up in 1084, that a couple of them went away in some form or another. I think there was one that was considered too advanced. We'll talk about that in a second, and it may have been one that was dropped, and at least one is kind of a commentary on another one, so they may have been merged or something. I'm not really sure about that. Um, but in any event, these were sort of the original collection there. And these 10 classics, particularly the 9 chapters on the mathematical art, were basically used throughout the for well before when Li Chongfeng assembled them until at least about 1600 or so when Western mathematics was starting to be introduced into China. So you have this period from the founding of Chinese society until about 1600 when there was very little conflict uh, conf- um, contact with the Western world, and so you had very little exchange of ideas between them. So here are the titles of them in Chinese and sort of I guess English translations. There you can see the Sea Island Mathematical Manual here, and you can see it was used to do some indirect measurement problems. So the shadow gauge manual there was an astronomy text. It was written probably somewhere around 100 BCE to about 100 CE. It does contain the Goju rule, the Pythagorean theorem, and it applied it to surveying. The most important of the classics was the 9 chapters on the mathematical art. That work in particular, all of these 10 classics, but especially the 9 chapters on the mathematical art, serves a role in Chinese mathematical development similar to the role the elements served in Greek or Western mathematics. You remember from our study of Greek mathematics that the elements of Euclid basically collected earlier works, earlier ideas, organized them in a really good way, and then that was used for training for this Greek axiomatic approach to mathematics for for centuries. In some ways, it's still the foundation of how we approach some things in Western mathematics. The 9 chapters on mathematical art probably evolved over a very long time. Some of this material probably goes back several centuries BCE. We know there was a commentary written in 263 CE, so it was basically completed by that time. So, I don't know exactly when it was all developed. Nobody really does, and nobody really knows who wrote it. It was compiled as we go along. Some of the results predate European discovery, and perhaps even those European discoveries may have actually eventually been copied from China. So things in the medieval period or early modern period there may have actually gotten some results in Europe from China. So the 9 chapters, here's sort of the title or what they're about. Chapter 1 is about land surveying. So it includes fraction operations, finding greatest common divisors, areas of triangles, rectangles, circles, trapeziums. It gives an approximation of pi there. Chapter 2 is millet and rice. So it has to do with types of goods and working with exchange rates. That involves proportions and percentages and fraction operations. Chapter 3 is distribution by proportion. So there it includes things like direct and inverse and compound proportions, arithmetic and geometric progressions, and dealing with money. Chapter 4 is short width. That deals with areas. Also, that goes along with that, extracting square roots. It even had some ideas about that we could interpret as being limit and infinitesimal ideas. So, foreshadowing some calculus ideas way before there was calculus. They dealt with quadratic and cubic equations in that chapter. Civil engineering is chapter 5. This was about construction problems involving volumes of solids and had a method of exhaustion similar to that used by Eudoxus and Archimedes. Chapter 6, fair distribution of goods, more ratio and proportion, problems related to traveling and taxation. Excess and deficit was chapter 7. They used the technique of double false position to solve some equations, including linear equations. Chapter 8, calculation by square tables. This included systems of simultaneous linear equations that were solved basically using matrix methods like, really just exactly the same as Gaussian elimination, centuries before Gauss, who lived in the 19th century. So I'm not sure when that chapter was written, but likely maybe before the first century of the Common Era. So very, very, maybe 1800 years before Gauss, possibly. Um, they had a chapter on right-angled triangles, chapter 9. That has the Goku rule, that is the Pythagorean theorem. They also use that. They use similar triangles and solving triangles, and it uses some quadratic equations. Now, everything in this was basically set up as a series of problems with methods for their solution. They didn't provide proofs for why their methods worked. Some folks later on in commentaries maybe went back and gave a little more explanation by why these solutions were correct and why they worked. But it was basically assumed if you're working through this, not only would you learn how to do them, but you would gain enough insight in by working through the problems and their solutions that you would just understand basically why they would work. And perhaps you could extrapolate from that. Okay, let's go on to the rest of the classics here. The Sea Island Mathematical Manual was written by Louis Hui in 262 of the Common Era. It has 9 problems, and it shows how to solve some indirect measurements problems. The Sun Tzu's Mathematical Manual was compiled and written around somewhere between 300 and 400 CE. Measurements are in there, and the use of counting rods to perform computations. The problems are similar to, but easier than, some of the ones in the 9 chapters. It does involve some solving congruences, which can be solved by the Chinese remainder theorem, something that is correctly actually named after the Chinese rather than some Europeans. So we'll talk about that maybe in a later video. There's another one translates as the Mathematical Manual of the 5 Administrative Departments, and remember these entire 10 classics were used in the training of civil servants, basically. So China had a very strong bureaucratic system, and they had these different parts of the government, and they needed folks to work and do the work of these different parts of the government. So the five departments were agriculture, war, accounts, granary, and treasury. Each one of those required some mathematics, and so this book here um, had a chapter for each of the departments and the mathematics you needed for those jobs. And so part of putting this together, um, this collection of the 10 classics, was to basically set up a curriculum for training civil servants. Then you have another couple more mathematical manuals. One was more problems like those in the 9 chapters, and another one had least common multiple and arithmetic progressions. And then there's one that says arithmetic methods in the 5 classics, and that was a little strange because it's a commentary on non-mathematical works. So the 5 classics there they're referring to are not 5 mathematical works, but 5 other important um, Chinese works, important not for their mathematics. Um, but this particular one does have some math questions in it, and particularly about calendar and large numbers. It has a method of interpolation in it. And another one of the classics is a continuation of ancient mathematics. This one was written by Wang Jiotong. Practical problems from the construction of dikes, dams, and other puzzle problems that didn't necessarily have an application. So, remember that these are just like the kind of uh, puzzle problems and practical and not so practical problems that you might find today in, say, an intermediate algebra or college algebra textbook. Notes on traditions of arithmetic methods. Su Yu, early in the 3rd century of the Common Era, was when that was written. Probably written, well, that's what they claim. It was written by him in that time, but it was probably written later by a different mathematician who used the earlier mathematician's name to try to give it some prestige or whatever. Um, at least that's a possibility. It's constructing very large numbers is one of the things that's in there. Then there's one on the method of interpolation, and this is a famous mathematician, Zhu Shongzhi. Includes a good approximation to pi, about 355 over 113. He does a volume of sphere, but this one is lost, and it was actually too advanced compared to the others, and it was eventually removed from the curriculum. So that could possibly explain why we went from at least 12 down to 11. The Art of 3 Degrees and Notation of Large Numbers by Dong Huan is another one. So ultimately, this is the collection that ultimately became known as the 10 Classics. And once again, these particular things were used to provide the basics for the curriculum. They had actually been used this way long before they were compiled into this collection called the 10 Classics. But especially from that point on, then they became basically the standard curriculum. That did a couple of different things. Since it was so standard, and it didn't encourage a lot of creativity from the mathematicians after this, because there was such a standard group of things that they thought people should use. Nevertheless, there was a lot of creativity by some Chinese mathematicians that were able to expound upon certain ones of these problems, add their new sets of problems after this, and do even more advanced mathematics as it went along. And there are several things that were the mathematicians in ancient and medieval uh, China did that predate similar discoveries in Europe, in some cases by a lot. We already mentioned the one about knowing Gaussian elimination way, way, way before Gauss lived, and knowing about, they knew about Pascal's triangle long before Pascal was ever born. So, kind of calling it Pascal's triangle is, you know, it's not really accurate. I mean, it is accurate that he used it a lot, but it's not accurate that he was the one that came up with it or even knew how to use it. So there are a lot of things like that that they were able to come up with on their own. But we think that once again that the Chinese uh, basically developed most of their stuff, most of their mathematics, kind of independently of the rest of the world for the most part, for a long period of time.